Okay, good morning, good afternoon, good evening. Today let's talk about how we can measure the phase and amplitude of different signals, mainly sine wave signals, using the FFT function. And this is a very common problem, either when you have many receivers that we need to calibrate or many DACs that you need to calibrate. Basically, we're going to go over a rather simple algorithm of how we can calibrate it and measure the gain and phase differences between different sets of hardware. And one approach is you feed a calibration signal into the many receivers that you're trying to align, or you capture the signals from many DACs and calibrate them through receivers. So here's a picture of many receivers, and we're sending a calibration tone to all of them, and now we're going to try to phase and magnitude align them. So for a very simplistic, let's just take two receivers here. So here we have the sine wave that we captured from two receivers. It's the same source, but as you can see when we plot the signals from the A to Ds, they're not equal. They have different amplitudes and they have a phase offset. So our method today is how do we measure this and correct for it? Well, the easiest way and the preferred way is to take the FFT of the two signals. And that's what we've done here. And since it was a real signal, that's why we see the negative frequency and positive frequency. For our case, we'll only use the positive frequency for this calibration. And to get the best accuracy for the FFT, we want the signal to be exactly in a FFT bin. And I call that the Bobby filter. And the math or frequency for that is if we want the bin to be in bin 100, it's 100 times the sample rate divided by the FFT size. Now it's in bin 101 because MATLAB is 1 based, so that's why it's in bin 101. If it was 0 based, it would be in bin 100. And I should say the 100 here is strictly arbitrary. So your FFT size, if your FFT size was 64, then obviously you may want to change 100 to 10, such that it shows up in filter 10. But in my case, I think the FFT size was 4096, so 100 is significantly less than that. So the signal will show up exactly in bin 100. Now, if you can't adjust this, it's not terrible. Just want to aim for the bigger FFT size. But to get the best accurate measurement, it is preferred to have the signal be exactly centered in a particular FFT bin. In our case, we chose it to be in bin 100 or 101 for MATLAB. All right, so now we have taken the FFT. We're going to take the max, or whatever the value is, at bin 101, and we're essentially going to get two complex numbers, and I designated them above as channel 1 FFT and channel 2 FFT. So the output will be two complex numbers, and we will show how using these two complex numbers we can compute essentially the dB and phase ratio between these two signals. And this is it. Most people take those complex numbers and separately convert them to gain and phase. I'm arguing to not do that. Do the ratio all in complex domain, and then once you have the ratio computed, then take the dB and phase. And I think you'll find that this will be a much cleaner way to compute it, and you'll have a lot less if statements to handle all the four quadrants. So how do we measure the dB and phase? Well, it's the ratio of those two complex numbers, and we're taking the conjugate of that ratio. And to get dB, it's 20 times log 10 of the magnitude, and phase is the angle. And if we want the angle in degrees, we multiply it by 180 over pi. And when we do that math, we see that the difference is 6 dB and the phase is 45. So a negative dB means that channel 2 is greater than channel 1. Positive dB means channel 1 is greater than channel 2. So channel 2 needs to apply 6 dB of attenuation and a negative 45 degree phase shift so that it matches channel 1. Now, most hardware can't understand what a negative phase shift means, so we do 360 minus 45 and we would tell it to apply a 315 degree phase shift.